check. 5 times 3 is 15. 15 minus 1 is 14. 14 over 2 is 7. That's correct. So this is equivalent to, for every epsilon positive, I will find a delta positive such that 0 less than will always imply, and I'm waiting for you to tell me what to write. I'm closing these markers all the time because they dry out very soon. I mean, for some reason, I used to go through one set for the entire semester. Now 3 sets are not enough per semester. Okay, ready? What do I have here? What do I have here? Anyone?
X minus 5.
Excellent.
It's x minus 5 because 5 is a, right?
Correct.
Okay.
And then it would be 3 halves x minus 1 over 2 minus 7.
That's it. That's our starting point. I will clean it up, find the least common denominator. So 3x minus 1, but minus 14, because the least common denominator is 2. So this is 3x minus 15 divided by 2. Always remember where we are going. That's our arrival. So what should I do next? What is next? And the only thing that I can do to that expression is, say it again.
Simplify?
No, I can't.
Isolate out of 3 halves.
No.
Yep.
Well, 3x minus 15 has a 3 in common, right? I have to get to x minus 5. So that is my target. So I know that somehow I have to get the x minus 5. Otherwise, I can't prove it. And at this point, I have to use the other property of the absolute value. The absolute value of a ratio is the ratio of absolute values. So I have to write this step. It's a mandatory step. You cannot take anything out of an absolute value. You cannot put anything in an absolute value. You have to write this step. Yes, now 3 is 3, the absolute value, and the absolute value of 2. What should I do next? To find delta. And remember where we are going. The target has to be on one side alone. So then what should I do to both sides to get the target on the left?
Multiply by 2/3.
Exactly. Thank you very much. And it's done. So therefore, delta must be, and there is nothing else possible, 2 epsilon over 3. Thank you very much. And of course, step 2, I have to write it. Show that delta equals, 2 epsilon over 3 works by reversing the above steps, or the steps from above, or the steps from 1. Even easier. Okay, you also asked for another numerical example. Let's see if we have in here another numerical example. Are they giving us, see, the graphs don't appear. That's my problem. For some reason, all of a sudden, I don't know if it was my printer or I have the old book here, so let's take a look. We're asked to use the graph, the given graph of f of x, the square of x, to find a number delta such that, so the numbers are not given, but they're giving us epsilon. We really don't need the graph for this one. There's no need, because they're giving us the function. So here it is. I'm going to graph it anyway, but it's the square root of x. So f of x equals the square root of x, and they're giving us 4, and what is the limit of f of x when x approaches 4 from either side? What could the limit be? Thank you very much. And the epsilon is given to us, so they give 2.4 up here, and they give 1.6. And of course they say if the absolute value of x minus 4 is less than delta, then the absolute value of the square of x minus 2 is, of course, less than 0.4, because, of course, epsilon is 0.4. The distance between 2 and 2.4, as well as the distance between 1.6 and 2. And they're asking us to find the correct delta. So, like before, in the other examples, we start with the end. And that is the end. So the square of x minus 2 in absolute value less than 0.4. Anyone remembers how to solve such a absolute value inequality? How do we solve this? In general, if I have the absolute value of x less than 5. So forget about this for a moment. How do I solve the absolute value of x less than 5? Anyone remembers how to solve this? Okay, so this is -5 less than x less than 5. So this is a compound inequality and also an absolute value inequality. Okay, so then I'm applying the same procedure here. So -0.4 less than the square of x minus 2 less than 0.4. How do I continue solving this? What do I have to do next? What is the next step? Excellent, very good. So 1.6 less than the square of x and less than 2.4. And I mentioned that before when we solved inequalities. I said you cannot square all three sides of such a compound inequality unless, so this is an exception, when I have a positive number, less than a positive number, less than a positive number, I can square those positive numbers because the resulting statement is still true, is still correct, but only in this situation. This is positive, this is square root is positive, this is positive. I will square all three sides. Square.
Professor, does that work if they're all negative?
You have to switch the inequality symbols, because now when you square the negatives, they become positive, and then you have to.
Yeah.
So that's why this is a very specific situation. Perfect question. So we know what 1.6. So 1.6 squared and 2.4 squared. I got 2.56 and 5.76. So 2.56 less than x less than 5.76. So at this point, I'm ready to find delta. So remember what we did in all these situations. We determined this x minus a. So in our problem, a is 4. So at this point, I will have to subtract 4 from all three sides. Subtract 4. In the middle, I have x minus 4. On this side, I have 5.76 minus 4 is 1.76. On this side, I have 4 minus 2.56, and I get negative, positive 1.44, right? So coming back to the graph, this piece is 1.76, and this piece is 1.44.
Why do we subtract 4?
Because we want a distance. Or, if you don't want to subtract 4, then you write here 2.56, and you write here 5.76, and it's the same thing. But we subtract 4 because that's what we are after. We're after x minus 5 or x minus 4 to find delta. Or just write the numbers, and you still have to subtract 4 to determine what that is. Right? So this would be negative, if you want. Still, we have to choose a delta, which is the smallest. So delta will be the minimum of two possible numbers, either 1.44 or 1.76. So which one is it? Obviously, we know the answer. 1.44. So when epsilon is 0.4, delta has to be 1.44. And with that, I would like to move on. I hope to be able to have a few minutes to finish up the quiz from last time, but I'd like to move on. So I promise I'll stop in 15-20 minutes at the most, and then we'll look at the quiz that we had last time to finish it up. I think we only had this quiz theorem in there. I think everything else is done. So 2.5, continuity.
Is there a 2.4 quiz?
I did not finish it up. I'm trying to put in a graph in there for you. I started creating it. I can show you. I can share the screen if you want. But I want to put a graph in there, or a function that is easy to graph for you quickly, so you don't have to, or put the graph in, something like that. So I will have 2.4 and 2.5 together, maybe, or two separate, 2 questions each for Wednesday. Thank you. Continuity. Let's start by looking at when a function is not continuous. How does it look like? A function that we say it's not continuous. Okay. So here are situations in which a function is not continuous. What do I mean by not continuous? I cannot draw it, for example, like this function. I can draw the function from the beginning till the end without lifting pencil, the marker off the paper. This is continuous. Here I had no choice. I had to stop here, lift, and continue somewhere else. This is called a jump. Discontinuity. Jump. Here is another. And you will tell me what do you think the name of this one is.
Professor, could you just show the last bit of the last page real quick?
When a function is not continuous. Is that okay?
Yes, thank you.
Thank you. Infinite discontinuity. And here's another one. And this one is called removable. Removable discontinuity. So jump discontinuity, infinite discontinuity, removable discontinuity. These two, the first two, cannot be removed. They will always be like that. I cannot create a function from what I see here. I cannot create a function that is continuous. I have no way of doing that. The same thing here. I have no way of determining or creating a continuous function from this. But here, I have a way of determining or creating a function that is continuous. Because I only need to change one point, a finite number of points. Here, it's not a finite. Here, it's not a finite. But here is a finite number of points that I can change in this function and create a continuous function. Only when the limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right. This is the condition for a removable discontinuity. Here, even if both sides go to negative infinity or both sides go to positive infinity, I still have too much to change, not finite. But here, it's a finite. Can I create a continuous function from this? Yes. I will say a function g of x, so this is our f of x. I will say f of x for x not equal a, and I will say L for x equals a. And now it's guaranteed. I fill this in. This function, I guarantee you, is continuous everywhere. I made it continuous everywhere by adding this value and filling in that point. So that is a removable discontinuity. Now we also have left and right continuity. Any questions so far? Any questions? So, left and right continuity. So the left continuity is the limit as x approaches a from the left of f of x equals the function value at that point. The right continuity is the limit of f of x as x approaches a from the right equals f of a. How does this look like? An example for both. So the left continuity will be something like this. The right continuity will be something like this. the limit from the left and the function value, of course, at a. The limit from the left and the function value at a are the same, so the function is continuous from the left. Here, the limit from the right and the function value at a are the same, so the function is continuous from the right. Any questions before we establish the biggest definition here? The biggest definition is continuity at a point. So, any questions? And now you'll tell me whether this function can I say that, oops, I didn't mean that. Can I say that this function is continuous at x equals a? Can I say that? What are the conditions for continuity at a point? 3 different quantities have to be the same. The limit from the
left
must equal the limit from the
right.
And definitely must equal
L. Oh,
we never had this condition before because we haven't talked about continuous functions before. We said the limit exists if the left limit and the right limit exist numbers and they are the same number. But now this is something else. This is a new concept. This is the concept of continuity at a value, at a point. So a function is continuous at that point if the limit from the right, the limit from the left, and the function value, they're all the same. And they all exist, of course. Any questions so far? I propose either looking at a function with a parameter to make it continuous everywhere, which is there are these 2 examples in the book, or going back to graph a piecewise defined function again. This is the 3rd one. I hope we don't have to do this too many times, and show whether it's continuous or not, or continuous from the left, or continuous from the right, or not at all. So which problem would you like to work on?